So this is chapter 7 and 8. Now, as I noted in the intro page that shows what we're going to do today, there are 4 principal theories of the atom. And these are referred to as, in general, atomic theories. Now, just to give you a bit of trivia, the first atomic theory that was actually published or made note of was made in 600 BC. By Democritus. I can't spell that, so I'm not going to worry. Democritus. Now, what he proposed, if you took a piece of matter, number one, and split it in half, and so you cut that in half, and then you took that half and split it in half, and then you took one of those halves or portions, split that in half, and kept going and going and going and splitting in half, you would eventually come to an indivisible particle. The operative word is indivisible here. In Greek, that's the atomos particle. And just as a matter of trivia, it is from that term, atomos particle, we get the word atom. And so from a fundamental standpoint, yeah, it started somewhere back in, but it was strictly a philosophical issue. These are significant because they're based on the scientific method. Scientific method. And the modern theories that evolved over the last couple of centuries are included. One, the Thompson plum pudding model. The Rutherford shell model, the Bohr concentric ring model, and the theory that we subscribe to today as the Schrodinger quantum model. So we want to talk about the fundamental foundations and postulates for these leading to the Schrodinger model and how we describe atoms in our present day concepts. So we'll start with the Thompson plum pudding model and then move through the others and showing you the fundamentals. Now, this theory and this concept evolved in the latter half of the 19th century, 1800s, late 1800s. And at that time, the scientific community understood concept, that is, this plum pudding model is based upon opposites attract concepts. That is, pluses attract negatives. That's what their concept was. I think we understood. And then like charges repel. That's the symbology for repulsion in some. Like charges simply repel, and they just kind of stay away from each other. What this led to was what we call the plum pudding model, and can be drawn simply in three-dimensional context. And Thompson visualized this as a spherical positive field. Like that, and in that positive field were embedded, negative electrons, and they were suspended in this positive field as shown in the general diagram. Now, the issue with this is there is no definition to the electronic structure. There was no definition of the idea of a nucleus. They did know that the atoms spit out negative charges, and they had in them positive charges in some capacity. And so based on just the simple opposites attract theory, this is the raisin pudding model. That is, the electrons are suspended in the positive matrix like plums in a gel pudding, and hence the evolution of that model. Now, there's other things to that. Now, what the scientific community saw in this was that if you had say a metal sheet, say of some dimensions, and composed of atoms that make up this system, then this entire wall would have a positive field around it. So if somebody came along and shot, for example, a positive charge at it, at that wall of atoms having a positive field, and like charges repel, they should see a repulsion and nothing would go through. Zero would go through that wall. Okay? Well, Ernest Rutherford and his group set out to prove that that was a true hypothesis. The evolution of the Rutherford shell model began with Ernest Rutherford trying to prove the Thompson model. And to do this, he set up a classic experiment that he won the Nobel Prize for. It's called the gold foil experiment. And so Rutherford's contention was that if he took a thin piece of metal, and what he did was hammered a piece of gold film into what he thought was as close to 1 atom thick sample as he could generate, and then he suspended that into a photosensitive chamber. And typically a photosensitive chamber has sensitive film that if light hits it or some radioactive substance hits it, then it would be exposed. Now what he planned to do here is he took a block of lead and placed in that block a sample, what we call an alpha particle generator. Or emitter, alpha particle emitter. Now an alpha particle is a helium nucleus without the electrons. And so that would be helium with a +2 charge. And so that's quite large. 2 protons, 2 neutrons with a +2 charge. And heavy elements like in the uranium level and the polonium level up in the 90s, well, they're natural emitters of alpha particles. And that's another story. But he lined these up so that these alpha particles would be directed to that gold foil. If the Thompson model was correct, then what would he observe? He would simply observe the reflection of the particles, and nothing would go through, and he would see exposure in wherever the particles would scatter back toward the source. Well, that's not what he saw, obviously. What happened was these 99.973%, as I remember, of particles passed through unperturbed. They were not affected one way or the other. But what he observed also was some of these particles went off on obtuse angles in that capacity, and he also saw some coming straight back at the source. And this was totally unknown in terms of what was causing this. And so the long story short, the results of this was that he postulated the shell model of the atom. And so the postulates, and they are in the outlines, if you go on the website and bring up the outlines, scroll down to the atomic theories that we're talking about, in that collection of notes is the postulates I'm about to give you. Well, first of all, the shell model is considered to be a spherical electron cloud with a very small, indivisible positive nucleus. hence the shell model as we recognize it today. It was a three-dimensional sphere, as he thought, with the nucleus in the middle, and the electronic cloud now had a kind of the negative field, where the Thompson model was all positive spherical field, but the center was an indivisible core nucleus. The significance of this revelation or hypothesis or postulate was Rutherford was the first to propose a two-part atom. Of course, that includes the nucleus plus charge, surrounded by the electron cloud having an overall negative field. And he had no definition, it's just this cloud around the nucleus. And the conclusions led to some of these explaining the observations. Say this is a collection of atoms of gold, nuclei in the middle here. The atom is mostly space, is another postulate. We've got a spherical cloud, but most of the alpha particles passed through unperturbed. They just went right through. It's like a cannonball going through tissue paper. However, there was a small percentage of the particles would come, he thought, close to this positive center and be repelled off at obtuse angles. But then there were some that went straight in and collided with the nucleus and came right back toward the source. So that was the experimental explanation on his postulates of how the atom behaved at the time. Now there are three calculations that go with this. Let me finish these, and then we'll take a break. Three calculations I want you to know about. One, what we call a distance relationship within the atom. So the purpose of this is if you had to describe to somebody what the atom looked like based on, say, the Bohr model, this would be a good set of postulates that you could work with. So we're talking about a distance relationship of atomic particles, of atomic structure. In general, one atomic diameter equals 100,000 nuclear diameters. So what I'm trying to teach you here is that if you selected an atomic diameter, say the size of a BB, maybe 1 millimeter, assume nuclear diameter equals 1 millimeter, about the size of a little buckshot or BB or something like that. Where would the edge of the electron cloud be? What would be, or I might say, what would be the radius of your atom? So, one atomic radius would then be 100,000 times the nuclear diameter, which is 110 to the 5th millimeters. That's your entire diameter. Okay, now that's kind of hard to visualize, so let's convert it to yards, something that's a little easier, feet, that's a little easier to understand. So 10 to the 5th millimeters being the diameter. Put the identity down, millimeters. And we'll go to millimeters, goes to centimeters, and centimeters goes to inches, and inches goes to feet. So you have the edge-to-edge distance given here. So there are 10 millimeters per centimeter, 2.54 centimeters in an inch, of course 12 inches in a foot. So those cancel out, and so we're saying 10 to the 5th millimeters is so many feet. So that's and so that's 328 feet across, and the radius, that's nucleus to the electron edge, is 328 over 2, half of that. So that's 164 feet. So what you're looking at is trying to describe something to somebody, and so you have this positive nucleus, and from here to here is 164 feet, and you have the electron, and then of course your nucleus right there. Well, what's between this? Mostly space. And so that's the second postulate, really, of the Rutherford model. The atom is mostly space. So, you know, it kind of gives credence to the Big Bang Theory. Everything can crush down to one massive piece of matter before it exploded. Okay, so what do you need to remember is this formula right here. One radius equals 100,000, whatever. You could choose a baseball size or a marble, 1 centimeter or whatever, and describe the atom in terms of, well, here's the nucleus and where's the edge of the atom. This is called the average atom. So you're comparing those two mass values. Well, there are things called rest masses. Yeah, here we go. Sorry. These are called rest mass values. And so you see electron mass, okay, 2 times that, and your proton mass should be in here somewhere. Proton mass here, so you got 2 protons, and you should have a neutron mass in here, and it shows 2 times that. They add them all up, and they come up with those numbers. And so just to give you an insight into where those come from. Now, of course, the percent of nuclear weight would be the weight of the nucleus over the weight of helium atom times 100%, and the percent of the electron cloud by weight is equal to the weight of the 2 electron over the weight of the helium atom times 100%. Well, to make a long story short, this comes out to be 99.997% by weight of the atom being the nuclear contribution, whereas the weight of the electron cloud is 0.003%, just be sure, for electron cloud, and this is the nucleus right here. So the point is that when Rutherford did the work on the atom and came up with a two-part atom, he didn't just say, okay, there's a nucleus and an electron cloud. His data led to real numbers that defined the mass relationships and the general structure of the atom, as well as the dimensions of the average atom. Now the last one, so what I'm asking you to remember is that this is a postulate of the Rutherford theory, that the nucleus comprises 99.997% of the atomic weight, and the rest of it's electrons, behavior, cloud. Now the question is, if we consider that it takes 100,000 nuclei to go across the atom to make a diameter of one atomic diameter, then you can ask the question, how many nuclear diameters does it take to fill up one average atomic volume? Well, there are data where you can calculate the volume of the nucleus based on Rutherford's work and volume of an atom, and then take the volume of the atom divided by the volume of the nucleus, and what you have is the number of nuclei per atomic volume turns out to be, let's see, one. That's 1,000 million. So my objective here is not to grind numbers into you, but to give you an appreciation of what Rutherford came up with in terms of the nature and character of the atomic models that he proposed. Now, we'll take a break here, and after the break, we will look at the third model of the atom, and it'll take the rest of the class. We call it the Bohr concentric ring model. This is the model that a lot of us grew up with, where you put a nucleus and a bunch of rings around it and dots for electrons. And so I'm going to show you where that came from and some basic calculations that go with this. If you notice, as we go along from the Thompson to the Rutherford to the Bohr and then the Schrodinger, it gets more and more detailed and more involved. So watch for that. Is what we call a bright line spectra of elements. Is a collection of bright line spectra.